Hello friends, welcome to lecture number 16 of Electricity and Magnetism, BSc Physics, and our topic of discussion is electrostatic potential. So before we start, please subscribe the channel, hit the like button, also hit the bell icon so that you get notified when new video will be uploaded, and inspire me to create new contents for you and stay connected. And link of the previous lectures are given in the description box from 1 to 15. So if you haven't watched those, please go through them. So now let's start. Now what is electric potential energy? So now you see, so this is the definition of electric potential energy. Potential energy of here, let me write the electrostatic potential energy of a charge q naught. So let me write this on here. Okay, electrostatic potential energy of a charge q naught at any point in an electric field due to any charge configuration is the work done by the external force in bringing the charge q naught from the infinity to that point. That means, let me explain. Suppose you have a charge here, positively charge q, and due to this we have an electric field, right? So electric potential energy of a charge, suppose q naught at a point, suppose p, will be the work done in bringing this charge from infinity to this point p, right? So that is the definition, right? So now let us consider suppose EV, the electric field due to a point charge q, another positive charge q naught is being brought to the point P from R by application of an external force lec-16, suppose, and it is just enough to counter the repulsive electrostatic force, right? Fe, and these two are opposite in direction. These two forces are opposite in direction. Suppose this is the q positive charge, point P, point R, and from point R to P, q naught charge is being brought to point P from R. Now you see, work done by the external force moving q naught charge from R to P is given by WRP. Integration from R to P, Fext dr is the displacement here. Now you see, if Fext is replaced by minus Fe, then this will be your expression, and this work done gets stored as an electrostatic potential energy, right? And this energy is equal to the potential difference between these 2 points, potential difference between P and R, right? So now let me go to the next slide. So let me write the last expression again. This is the last expression we have got, right? So if UP is the electrostatic potential energy at P, suppose, let me modify this, electrostatic potential energy at P, and WR is the electrostatic potential energy at R. Potential energy at R, then, so here is the, let me draw the diagram again here. Just wait, let me erase these things. Okay, so here is the diagram. Q naught is brought from R to P, right? So potential energy at P is UP, and that at R is UR. So now work done, this work done will be equal to del U, that is the difference, potential energy difference between these 2 points. So now if R is at infinity and where potential energy is 0, right? So potential energy is 0 means here you see this dotted yellow line represents suppose electric field. Then if R is at outside the at a point, R is a point suppose outside the field, then outside the field there will be no electrostatic potential, right? So now potential at infinity, you can write UR, let me write here instead of UR, let me write in U infinity, okay, where potential energy is 0. So work done in bringing this Q naught charge from infinity to point is given by this work done, right? Work done, this work done in bringing this Q naught charge from infinity to a point P will give you the electric potential energy of this charge Q naught at this point P, right? So this is the electrostatic potential energy of Q naught at P. Now what is electrostatic potential at P? So electrostatic potential at the point P, and that is Vp, will be given by work done to bring the Q naught charge from infinity to T by Q naught. That means the electrostatic potential energy, electrostatic potential at a point in an electric field is the amount of work done in moving a unit positive charge from infinity to that point, right? So that is the against the electrostatic force. So that is the electrostatic potential at that point. So that as you can see that in order to bring Q naught charge from infinity to P, we have done this amount of work, W infinity P, right? So what will be the work done to bring one unit charge? That will be given by W infinity P by Q naught, and that is the potential at that point where we have kept the Q naught in the electric field after it is brought from infinity to that point, right? So hope you have understood this. This is about electrostatic potential due to a point charge. Now you see, suppose this is a point charge Q, and at a point A which is in the electric field due to this point charge Q, at this point A there is another test charge, let it be Q naught, right? So its position vector is suppose R, this is the position vector R, right? So now you see this Q naught charge is moved radially towards Q. Before that, let me tell you one more thing. The force experienced by this Q naught due to this Q, the electrostatic force Q naught on Q naught due to Q is given by F is equal to 1 by 4 pi epsilon naught Q into Q naught by R square. This is given by Coulomb's law, right? Now this Q naught charge is moved through a very small distance dr against this force F, electrostatic force F, from this A point to point B. Suppose this is the point B and this is the point A, right? So through a very small distance dr it is moved, right? Now let us consider these two charges Q and Q naught, both are positive. Suppose this Q naught charge is moved through a very small distance. Let me write here Q naught charge is moved through a very small distance dr radially. So this q naught charge is moved from A to B in radial direction. This is if you imagine a sphere here, so along the radius of this this q naught is moved, right? So now you see this q naught is moved in this direction, and as the q and q naught both are positive, so this is the direction of dr, then the direction of the electrostatic force will be opposite to it, this direction, right? So here you see angle between these two angle between these two vectors, the electrostatic force and the displacement vector dr, that is 180, right? That is 180 degree. So now let me go to the next slide. Amount of work done, test charge q naught through a very small distance, through a very small distance dr, through very small, instead of writing distance, let me write here displacement, very small displacement dr, right? Let me go to previous slide. Let me make a correction here. So let me write here, instead of distance, let me write here displacement. dr. Okay. So now amount of work done in moving the test surge q naught through the very small displacement dr is dw is equal to f dot displacement dr, right? And this electrostatic force F is in opposite direction, right? So this is acting in opposite direction, and the displacement is in this direction, right? So angle between them is 180, right? So dot product of these two, F dr cos 180 degree, right? As the electrostatic force F acts away from q naught, right? So cos 180 is -1, so we will get minus f dr, right? And value of f from Coulomb's law, we have already got that f is equal to 1/4 epsilon naught q naught by r square. That's what we have got. Now let us replace this by that value. So minus 1/4 pi epsilon naught q naught by r square dr. That's what we will get, right? So now you see, let me take the diagram that we have drawn in the first slide. Let's do it in the next slide. Let me write dw here. So now let me copy this expression. So the last expression we have got is this. So this is the work done to move q naught through a very small displacement dr. Now you see the diagram we have drawn is this. This is a q small positive charge point charge, and a test charge q naught is brought from A to B through a very small displacement dr, right? So now instead from A, this here you see A and B both are in this field due to this q positive charge. Now let us consider, instead of bringing this q naught from A, it is brought from suppose infinity. Then what will be the work done? So work done work done in moving q naught, in moving the charge q naught from, so let me write here, q naught charge from infinity to the position which is at a distance of r from q, right, to this point. This is the position vector r. Suppose, let me take that one, right? So should just let me write here. Okay, from infinity to a point, let me write here, to a point with position vector r with respect to q is w is equal to, if we integrate dw from infinity to r, then we will get the total work done, right? So that will be equal to infinity to r. So here we have minus 1 by 4 pi epsilon naught q naught by r square dr. That's what we will get, right? So now you see, here we can bring the constant terms out from the integral. So q naught by r, sorry, not by r, this is r is variable in this case now, q naught integration 1 by r square, so infinity to r dr, right? So this is the total work done, w. Now let me go to the next slide. Okay, so here is the expression that we have got, right? So now if you integrate 1 by r squared, that's going to be minus 1 by r, and so this minus will be plus on after integration, that is 1 by 4 pi epsilon naught q naught. Integrating this, we have got minus 1 by r, and because of this minus it becomes positive, so here it will be 1 by r. Integration of 1 by r square is minus 1 by r, right? So from infinity to r, that's what we will get, right? So now you see, if you haven't understood, then let me show you. 1 by r square dr, 1 by r square can be considered as r to the power minus 2 dr, so it will be r to the power minus 2 plus 1 by minus 2 plus 1 dr. Sorry, here dr should not be written after integration. Okay, that will be r to the power minus 1 by minus 1, that's minus 1 by r, right? So because of this minus and this minus, that's going to be plus, right? So now w is equal to 1 by 4 pi epsilon naught q naught. If you put r, we will get 1 by r. If you put infinity, minus 1 by infinity. So 1 by infinity is 0, so our result is 1 by 4 pi epsilon naught q naught by r. So this is the work done, total work done. So now potential at this point, here you see, this is the charge, suppose that this is the charge, point charge q, and q naught is brought from infinity to this point, which is whose position vector relative to q positive is suppose r vector. So at this point the potential is nothing but the work done per unit charge to bring this in moving this from infinity to this position, right? So that's why the electrostatic potential at the point P, sorry, not P, A. So the point A we had taken with position vector r. Therefore the electrostatic potential at the point A is given by V is equal to W by Q naught. That's going to be equal to, if you divide this by both side by Q naught, then this Q naught will be cancelled, right? So then what you will get, 1 by 4 pi epsilon naught Q by R. That is the potential, right? That is the potential at a point with position vector R relative to relative to a point source Q positive, right? So hope you have understood now. See you in the next video. Please inspire me to create new contents for you. Please subscribe the channel, hit the bell icon so that you get notified when new video will be uploaded. If you think that my videos are helpful, then please share with your friends, and see you in the next video. Thank you for watching.